Okay, let's start. Any questions from anything that we discussed till now? No? Yes.
So, at some point of time, you had changed the polarity of the two terminals just to make the negative feedback.
Right.
So, my question is that in the actual op-amp,
Right.
is that performance done by a separate functional block to change the polarity, or like sir, for negative feedback we directly connect. So we connect the negative feedback part in the negative terminal. Right. So is there any internal block diagram?
Okay, so okay, let me address this. I mean, what he is saying is that if you have gone through the previous lecture, you would have seen that there was a case where let me go back to that notes. I think it is fine. Helpful. I think here, right? Yeah, so we had changed the polarity of these, right? We had changed the polarity of these because we said that if you go around the loop, it becomes positive feedback. So his question is, I mean, if we take the example of a real, ideal op-amp also that we are so used to, we always seem to connect the output to the negative terminal. Okay, but that need not necessarily be the case, because what if there is another inversion in that loop? It might be another transistor, maybe another something. There can be an inversion in the loop. So it might so happen that whatever you mark it as positive for the op-amp might end up being the negative terminal for the overall feedback. Right. So essentially what you have to be aware of is what is the sense of the overall loop. Okay. Yes.
So in the expression of LS, so it was generally negative of V written by V.
Right. Yeah.
So the expression that you have derived as GM by SCK for this after changing this terminal, like signs.
Yeah.
So will there be a minus sign, or it's a
V return will have minus. V return voltage will have a negative sign, and L of S is minus of V return by.
So sir, in that expression, there will be minus sign, that GM by SCK.
Return voltage will have minus.
GM by SCK, this expression. LS.
No, right? Why will LS will be positive? The return voltage will have a negative, right? Why do you say LS will be negative?
Sir, actually, in the earlier case, there was a negative sign because of the feedback was connected to the negative terminal.
Now it also will have a negative because you have there's a double inversion here, right? So because I have changed the polarity here, and I have also changed the, I mean, this op-amp, if you see, I mean, this block that you see here, right? So this is also inverting, right? So overall, nothing has changed as far as the signs are concerned. Okay. Okay, so before we move out of this block diagrammatic representation or partially move out of it, let me address some of the couple of important things that you need to know while breaking the loop, right? So let's go back to the good old block diagrammatic representation. So here we said that how do you figure out what is the loop gain? You can break it at any point and apply a test voltage and see what is the return voltage, and then you do minus V return by V test. Okay, but that's not the full story. So why is it not the full story? Because I intentionally or very conveniently broke it at some strategic places. I showed that I can break it here, or I can break it here, or I can break it here, and everywhere you are getting the same loop gain, right? Because loop gain is supposed to be the property of the loop, and it should not depend upon where you break it. But let me do something different. Let me break it here. Okay, that's also a part of the loop. I can break it there. So let me break it there. Pull this out a bit so that the so I break it here. So this was the term, this was the connection. I broke that connection and I apply a test voltage. And from whatever we have been doing, at which point should we be checking the return voltage? Where we have broken, right? So we should be checking the return voltage here, right? So now go around the loop and tell me what is the return voltage. Yeah, so the return voltage is minus V test omega u by S, right? So which means that the return ratio, or even, I mean, this L of S in this case is omega u over S. So this is supposed to be omega u over Ks, right? We have been doing omega u over Ks for last couple of weeks. So why do you think this is different? Pardon? Feedback is not happening. Okay, so yeah, correct. We are hampering indeed. How? Right. Okay, yeah. So his point is correct. He's saying that, I mean, we were getting there was a voltage division happening at that point. At the point we are actually checking the output. In the previous configurations, when we actually broke the loop at other places, there was a voltage division that was happening. But by breaking this, we have tampered with that. So that's why we are not getting the factor of K. Do you agree? Okay, so that is correct. Now this is particular to this particular circuit, right? This is an example particular to this circuit. So if you have to generalize it, that statement can be generalized as saying that we have affected the loading. Pardon? Okay, why will it come? Yeah, so fine. So you are contesting this expression, right? Okay, tell me why. Yeah, according to you, what should be this expression with the configuration that I have shown? Okay, so here it's fine, right? You say it's omega u over S times V test, right? So here it's omega u over S V test negative sign. Why should you multiply? That's the question. I mean, is a resistor a multiplicative thing? No, right? It's not a multiplicative transfer function, right? So the way I have shown it, it's open loop. It's opened. So which means whatever, no current will flow. If no current flows, whatever voltage you have here, same voltage you'll have here. Okay. So essentially that leads to the final, I mean, that leads to the conclusion of what is wrong with this type of breaking. So we have tampered with the normal operation of the circuit. We have tampered with the loading, right? So what is this omega u over S supposed to be doing? Omega u over S was supposed to be supplying current to these resistor stack of K minus 1R plus R, right? Overall KR was supposed to be loading the omega u over S block. Okay. So now by breaking the loop, we have essentially told that omega over S block that no more effort is required because we are not drawing any current. But that's not the purpose of breaking the loop. What is the purpose of breaking the loop? The reason we want to break the loop and do an analysis is because we want to extract or infer how the closed loop behavior will be, right? So if we tamper the loop in certain way that the loading itself gets hampered, which means that we'll not be able to get the correct information necessary to figure out what the closed loop response will be. Okay, so the key thing is to ensure that the loading doesn't change when you break the loop. So if I have to then modify this circuit after breaking the loop, I still insist that I'll be breaking the loop at that point, but I want to modify in such a way that the loading doesn't get affected. Then what should I do? Which essentially means that I should be drawing the same amount of current from the node V0. right? In other words, it means that omega v over S block, or the block that is preceding that node, should be providing the same amount of current. Okay, so which means that the loading should be same before and after breaking the loop. So what was the load seen by omega over S before breaking the loop? KR. What is the load that it's seeing now? It's not seeing, it's infinite, right? The other end of the K minus 1 is dangling. So what should I do to ensure that we still have KR load at the output of omega over S? Yeah, so essentially whatever was broken should be reattached. Okay, so essentially what we need to do, we need to reattach this R here and then observe this return voltage. Okay, then it becomes fine. Okay, and note that since we have applied a detached voltage at the place where I have shown, having this R or not having this R doesn't make any sense because we have added an ideal voltage source in parallel to it. Okay, so you can as well remove this R and say that the initial R was translated to the other side. Okay, so in general, if you have any circuit, maybe you have some feedback circuit. You have a block, this is connected somehow, and you had a feedback between these two nodes, right? So forget about this. So there was supposed to be a feedback in this line, and I want to break it here. Okay, so the first thing then I need to see is, I mean, let's say this is unilateral for the time being. I mean, if it's bilateral, then you have to take more things into consideration. Let's assume it's unilateral, and let's assume that the input impedance looking here is Ri, and the output impedance looking here is R0. And I want to break it at the location I have shown. Then what I have to do is, firstly, obviously, I have to break it and apply a test voltage. But I have to ensure that the loading of the return side is maintained. Okay, so which means I have to translate this R0, Ri here. Okay, then I go around the loop and do whatever I want to do. So this is what you do if you have to break and apply a voltage source and see the return voltage. So I'll not get into the case where, I mean, you can also argue that why voltage source, we also have a current source. Right? I can as well apply a test current and then figure out what is the return current. There is nothing holy about applying a voltage source. This is just another source. Yes, you can do that. In that case, you have to change the loading differently because, I mean, a current source can have, you can have Ri when you have current source, but the return current has to be a short circuit. So those things we'll not get into. For the purpose of this course, we'll just presume that whatever circuits we will be delving into is good enough to be analyzed using while we break and apply a test voltage source. Okay, but you'll have to be, so essentially the moot point is that you have to be aware of the fact that even though loop gain is a property of the loop, or the return ratio is particular to a loop, when you break the loop, ensure that the loading is maintained. Okay, any questions? No? Yes.
Earlier when we were breaking the loop, this was taking care of it.
Yeah, so earlier when we were breaking the loop, that's why I said I strategically broke the loop here. So because there was no effect of loading in this case, right? Because there was, here the input impedance was infinite. Okay, if the input impedance is infinite, translating that infinite impedance to the other side doesn't make any difference.
After shifting the resistance to that point, it doesn't seem like we have tampered.
Exactly, we should not be tampering with the loop, right? So the operation of the loop should be such that the loading at each point, each node of the loop remains untempered. Okay, so that's the whole purpose of it. So sometimes you'll see that in some circuits, it's easier to find a location where it's, even if you break it without taking care of the loading, things are fine because maybe it's a high impedance node. If it's a high impedance node, you probably don't bother because nothing needs to be translated and it's fine. But in some cases, you will find that it's not high impedance. So you'll have to take into account these things. And truly speaking, when you are designing circuits with transistors, there is no node which is exactly infinite impedance, because even if it's like even if you are seeing the gate of a transistor, you are seeing some capacitance. At high frequencies, capacitance will also draw current. So strictly speaking, you have to translate that capacitance on the other side also. But again, I mean, those are discussions for another course. We'll not get into that.
So,
yes.
If the input impedance of the integrator is not infinite,
yeah,
in that case, will there be any issue?
That's what I just said, right? If it's not infinite, then you'll have to translate it back. I mean, if let's say you have an input impedance here, right? So let's say Z in, and you break the loop where it's marked right now, then obviously you'll have to ensure that a Z in appears here after breaking the loop, right? So yeah, so that's a generic way of breaking the loop using voltage sources. Okay, any other questions? Okay. Okay, so then let's proceed. And while we end at the end of the previous lecture, we had replaced the integrator with the voltage controlled current source and a capacitor, and this was VE. And we had a VCVS also of factor alpha. So this is V1. Okay. So as it turns out, I mean, for reasons that will be clear later on, we don't really have the luxury to use a VCVS in the technologies that we use nowadays. It might not be clear now. We'll address that later. Take it at a face value that let's assume that we'll not be able to use this VCVS. Okay. So if we are not able to use this VCVS, then the other option is just to simply connect these two. Okay. So now if I connect these two, okay, I messed up the signs. So this should be this way. So if I simply connect these two, what do you think changes? Okay, instead of asking what do you think changes, let me simply ask you find out loop gain. Wherever you want to break, you break and find out the loop gain. Okay, so I saw many of you got GM by SCK, and somebody who got GM over SCK, can you walk me through the reasoning? Okay, yeah, correct, right? So essentially, see, I mean, it's different from what I have been doing earlier. I mean, let me break again at the most convenient points, maybe here, because I don't have to bother about loading. We test. This is V test. Now, this current that comes out of it, right? This current that comes out is GM times V test, right? So, but this current is now not only going into the capacitor. This capacitor is coming in parallel to this entire stack, right? So that's why I saw many of you didn't actually physically break the loop. So physically break the loop to do the loop gain analysis. Otherwise, there can be misinterpretations of many things. Okay, so it doesn't take much, right? So redraw it, break it, and then figure out what is it? What is it that is different? So if I take this loading into account, then what is V naught? What is V naught? Minus V test into GM into, or rather GM by the conductance. The conductance is C plus 1 by KR, right? SC plus, yeah, correct. Yeah, cardinal sin. Okay, SC plus 1 over KR, right? So, and this gets divided by factor of K when it appears at the return terminal. So your LFS is GMR by 1 plus SCR times K. No, something is wrong. No, this is fine. This is fine. Yeah. Yeah. So one way to quick sanity check is if you tend R to infinity, right? Then there is no loading. If you tend R to infinity, you get GM by SCK. Okay. So that's what is getting pointed out here. So what is the DC gain of this loop? GMR. And what was the DC gain of the earlier integrator when I had another voltage control voltage source buffering this VCCS? It was infinite, right? So now if I have to sketch this, on a Bode plot, what will it look like? It will be constant, and this constant will be what at GMR, right? And then it will break. It will hit a pole. Where is the pole? And after that, it degrades by 20 dB per decade. So what is the other most important thing that I need to look for in this negative feedback loop or in this loop gain? UGV, right? And what is the UGV? Assume GMR to be much greater than 1. What is the UGV? Somebody from that side? So what is the expression of this line, straight line segment? Or what is the, how can I, yeah, what is the expression of that straight line segment? For Bode approximation, if I use, what am I essentially saying? Yeah, so this, if I use a Bode approximation, if it's of the form of 1 by 1 plus S by P, and I'm operating at omega greater than P, what does Bode approximation tell us? I can neglect that 1 plus, right? So if I neglect that 1 plus, this straight line segment can be approximated as GM by SKC. Okay, so if that is the scenario, then what is this omega U loop? Right, so this is my. So with respect to an ideal integrator, what has changed and what has not changed? Or in other words, when I say ideal integrator, I mean that this VCCS with capacitance was buffered with a voltage control voltage source, right? So what has changed? DC gain clearly has changed. What has not changed? So in other words, if I say that I am sketching that again, the same ideal integrator stuff. So I have three options of sketching. I can sketch it like this, I can sketch it like this, or I can sketch it like this. So which one is the right one? The question is, if I had the case where there was a buffer in between, right? An ideal integrator case where we had a buffer here, right? We had a voltage buffer here of gain 1. So in this case, how is that case similar and different from the case that we are dealing with now? Okay, so ideal integrator will have a slope of minus 20 dB per decade, right? So among these three colored lines, which one do you think represents that case? Red one. Okay, why? So what will be the expression for the red line or magenta line? Look at your notes and tell me. You have been doing it for like last 15 days. Pardon? Alpha equal to 1. Right, yeah. So if alpha equal to 1, then it becomes GM by SKC. Right? So which essentially means that it should be flush on the slope of the real case. Okay. So which means that we should be getting the blue line. Is that correct? Or are you convinced? Not convinced? If you're not convinced, we can do it again. So are you convinced? Yeah, exactly. All the three lines have the same slope, but what is the expression? All the three lines we have 20 dB per decade slope. That's correct. But where will it cut? Essentially, the question is where will it cut the UGB? Okay, that's the backhanded way of asking.
So for the magenta line, it is alpha greater than 1.
Right.
Green line is alpha less than 1.
Okay. Okay. So let me go back to the old one. So the L of S in that case was alpha GM by SKC. Okay. So we had the buffering, we had broken the loop, and then it's not about breaking the loop. We had essentially said that you have this transconductance loading a capacitance that is forming the integrator, but the integrator is not directly seeing the resistor stack, right? So it was being buffered by a voltage controlled voltage source, and the voltage controlled voltage source gives you infinite impedance. So there was no current sharing between the capacitance and the input side of the voltage controlled voltage source. Now, if I remove the voltage controlled voltage source, clearly the resistor stack of K minus 1R plus R, that is KR, comes in parallel to C. Okay, so which means that it will load, and that loading effect is evident. Why? What purpose? Okay, we are in the middle of the class, right?
I thought maybe quiz might go.
Not here. It will be. You can sit here if you want. So, so the loading effect is visible here. However, as you go at higher and higher frequencies, what essentially happens is the capacitor starts dominating the impedance. So most of the current then starts going into the capacitor. At DC, most of the current would prefer to go into the resistors. At high frequencies, most of the current would prefer to go into the capacitor. And what is that break point where it prefers capacitance or resistors? That break point is a pole location. 1 over RC, 1 over KRC in this case. Okay, so before you hit that pole location, the resistor stack gives you lower impedance. After you hit the pole location, the capacitor gives you lower impedance. So the current prefers to go into the resistor stack before you hit the pole in terms of frequency, and it prefers to go into the capacitor after you hit the pole. Okay, so which essentially means that after you hit the pole, there is no difference between this configuration and a configuration with an ideal integrator. Okay, so that's why these two lines match after you hit the pole. Okay. Any questions?
So, sir, this can be used as a voltage control voltage source after this.
Yeah, exactly, right. So his point is, then it seems like this configuration can be used as a voltage control voltage source after I hit the pole, because there seems to be no difference between what was happening if I had an ideal voltage control voltage source and what is happening now. Okay.
Sir, this is a kind of difference, like beyond the pole, the frequency is so as the capacitive current is so large in compared to the current that is passing through this.
Right, exactly. Yeah. So I mean, it's the low impedance path through the capacitor, so current prefers capacitance.
So
current path prefers
like an ideal case.
Correct. Exactly. Okay. Any questions? Okay. So now I'll not get into how the closed loop behavior will be. I'll not derive it, but without deriving anything, can you tell me approximately what the closed loop behavior will be? What will be the closed loop H of S essentially? How will it look like on this Bode plot? If GMR is much greater than 1. So I don't want to do any maths. From whatever argument we had been harping on for the last, I don't know, 48 hours. Yeah. Yeah. So let me ask somebody from that side or this side. So when does negative feedback work? What 3 dB frequency? In terms of loop gain, looking at the loop gain, how do I know till what frequency your negative feedback is working? What is constant? In loop gain, where, okay, so you mean till 1 over KRC in this case here. But if you have an ideal integrator, it is never constant, right? So 1 over KRC is at 0 frequency, then, right? R is infinity. So when does a negative feedback loop work as you want it to? Yeah, I want to look at the open loop and interpret closed loop response. Okay, so looking at the open loop response of loop gain, where can I draw a crude line and say that negative feedback works till this frequency? Yeah, before omega u loop, right? Because when does negative feedback work? Again, I mean, so works when mod of L of j omega is greater than 1, right? So that is the crudest assumption. Okay, so that is why negative loop gain is vital, right? So if you take this assumption, then till what frequency negative feedback will work? It's where this L of mod of L of j omega is the 0 dB line, right? So this is a 0 dB line till here. So if it works till that frequency, okay, what is the expected output? Expected closed loop output, or expected V0 over Vi in a closed loop scenario? Exactly, right? It will be stable. It will be constant till K. Constant It will be constant, and I expect a gain of K, because that's what we have been doing for last 5 weeks. And after that, it will drop off. Okay, and it will drop off at 20 dB per decade. Okay, but note that this will not be exactly K, because I don't have infinite gain. Okay, so at DC, what will be the steady state error?
Approximately 1 by mod of loop gain.
Yeah, approximately 1 by mod of loop gain, right? So, yeah, so you see the loop gain is not infinite, so your steady state error will be of the order of 1 over GMR. Okay, so in terms of the ratio of what you expect it to be. Okay. Okay, so the last thing that I wanted to talk about is the fact that if you look into this configuration, so why were we looking into this configuration? We are looking into this configuration because ultimately we would want to replace everything with a transistor, and this seems to be a very basic transistor model. Okay, but this doesn't capture one thing, is the fact that we'll never get a case where the conductance, output conductance is 0, right? So in a real transistor, what you saw was there was GDS, and the GDS can be, it depends on the biasing conditions, right? You saw that GDS is proportional to I naught. GDS is also proportional to lambda, where lambda is dependent on the length of the transistor, and so on and so forth, which essentially means that we have a GDS and we cannot really wish it away. So what is the effect if we have a GDS on the loop gain? And let's assume that you have a buffer, I mean, to make life simple. What is the effect of this GDS? It will load the capacitor. It will be exactly the same thing that we have been observing. So what will be the loop gain now? What will be loop gain? GM by, I mean, I break the loop again. I break the loop here. You have to desensitize the input, obviously, because when you are doing loop gain, input doesn't have any role to play. Again, I messed up the signs. Okay. So this is V test. So tell me, what is the loop gain? Somebody from this side.
SC plus
GM divided by SC plus GDS. Yeah, yeah. So, so if this is the loop gain in the presence of GDS, so what will be how will my mod of L of S get affected? So it's always useful to write it in the form of something by 1 plus pole, right? So that way you don't have to massage it further. So I'll just take out GDS and K out. So GM times K. Okay, so in this case, your DC gain is DC gain of the loop, right? Not the DC gain of the transistor. The DC gain of the transistor in this case is GM by GDS, but the DC gain of the loop is GM by GDS over K. So this is GM by GDS over K, and you hit a breakpoint at GDS over C, and it drops down at 20 dB per decade. And what will be this location? Omega U loop. No, it won't be GDS by C. It will be the same good old thing, right? GM over KC. Right? Again, I mean, if you assume you have hit the pole and you are, you again do a Bode approximation, which means that AC terms dominates. So this expression becomes GM by KSC, and you hit the UGB at GM by KC. Okay, so so the moot point here is that, I mean, the thing that I'm harping on is the fact that after, it doesn't really matter what type of what is there, what is a DC gain. The DC gain has no bearing on the location of omega U loop, as long as the DC gain is high enough. If you make your GM by GDS less than 1, then you never hit omega U loop, right? Because everything is less than 1. But assuming that the DC gain is more than 1, much more than 1, then it really doesn't matter where the omega U loop is, because it is far away from the pole, low frequency pole of the open loop system. That is number one. Number two is your DC gain. As we saw in the previous classes, that DC gain essentially dictates the steady state error for DC inputs, right? For step inputs. So which means that there will be a difference with respect to an ideal integrator case and when you have a non-ideal integrator. And if you are particularly concerned about applications where you want to reduce the DC steady state error, then you have to ensure that this ratio of GM by GDS is high enough. Okay, so if I have to make GM by GDS high, okay, so what I mean is we had so this was the model of our transistor, right? So our transistor was modeled like this. And this is only the incremental model. I'm not showing the bias. If I only bothered about DC gain, the DC gain of this is GM by GDS. Okay. And why is, I mean, if I have to go higher and I want to keep the same GM, okay, so which means that I have to reduce GDS or I have to increase the output impedance, right? So essentially the output impedance here R0 is 1 over GDS. So what configuration, I mean, you have already done a couple of assignments. What configuration comes to mind that will help us in increasing this factor, increasing this output resistance? recall the assignment 1, there were many. Adding another resistance to the source, right? So adding another resistance to the source. If I add another resistance to the source, let's say this is R1. So what will be R out if I add this? Yeah, so it will be R1 plus 1 by GDS plus GM R by GDS. Okay. So in this case, if you assume that this factor of GM by GDS is more than 1, because ultimately when we are making a transistor, we expect this ratio to be more than 1. So which terms do you think is dominating? So this term of GM over GDS is more than 1. Okay. If this is 1, then this is R1, right? So if this is more than 1, and if I also make again the assumption that GM over R is more than 1, R1 is more than 1, then clearly the third term is dominating. Okay. So it looks like this if I just stick a resistor at the source of my transistor, the output impedance increases by a factor of GM times R1, right? So if I assume this to be approximately equal to 1 over GDS times GMR1. So it seems like initially I had a output impedance of GDS, but now the output impedance has increased by a factor of GM times R1. Okay. Does that make sense? Now, if that makes sense, which essentially means that we have a handle of increasing the output resistance, but the issue here is that what is the effective GM? Or how do you figure out what is the effective GM? You essentially short the output and figure out what is the short circuit current, right? If you figure out what is the short circuit current by input voltage is the transconductance, right? So in this case, what is the transconductance? If I short the output and figure out what is ISC. So ISC by VI, what is ISC over VI? And this was a part of the assignment that you submitted today. GM upon 1 plus GMR1, right? So, and we assume that GMR1 is more than 1. I mean, if we assume that, this approximately becomes equal to 1 by R1. Okay. So as you see that this is obviously less than GM because we initially assumed that GMR1 is greater than 1. So if we just add a resistor R1 where we have added it here, we are able to increase the output resistance, but at the cost of reducing the GM, right? So what is the intrinsic gain now? What is the effective? So intrinsic gain. So let's say, let me call it capital GM. So this was capital GM. So that is capital GM into R out is approximately equal to what? Effectively GM over GDS, right? So intrinsic gain doesn't really change, right? If you use this configuration. So we'll see in the next class what we can do to address these issues. Okay, so